Hi everyone, welcome back. Sasha Townsend here. This is our first video covering section 1.1, which is about prerequisites for section 1.1. Chapter 1 is all about logic and proof. This material is so important because after learning logic and proof, you're going to be able to prove things. You're going to be able to follow proofs that you read in calculus books, proofs that you read in other books. You're going to understand how to think the way a mathematician thinks. And that's going to help you in all areas of your life. So just as a quick recap of what we talked about last time, inductive reasoning is a type of reasoning that we do when we make observations of what is happening in the environment, and then we come up with a theory or a law to explain those observations. And then after coming up with our theory or law, we typically would come up with some kind of experiment and say, if our theory or law is true, then when I run this experiment, these are the types of observations, that I would expect to see. And if the results of that experiment produce observations that are consistent with the theory or law that we've come up with, we might say that law or theory is pretty sound. And the problem with this type of reasoning is that one more observation that contradicts all of the overwhelming evidence that you have so far means that your theory needs to be perhaps thrown out or maybe just not modified. That is the type of reasoning scientists engage in most. Now, mathematics is characterized by what's called deductive reasoning. Now, mathematicians use inductive reasoning as well. That's pretty much how I start every problem. If I'm trying to figure out sort of the lay of the land when it comes to a particular mathematical, I'll just say, landscape. Often what I do is I plug in values for n or plug in values for x, and I'll typically start with small values for n, and then I will also look at a number of large values for n, and I'll try to infer some pattern, try to have, come up with some guess about what's going on. So when I do that, what I'm doing is I'm engaging in inductive reasoning. I'm coming up with some theory for how these mathematical objects work together and influence each other. Now, the difference between a mathematician and somebody in STEM is that when a mathematician comes up with that conjecture, they're not satisfied with just conducting some experiment and finding more observations to support the conjecture. As you gain more and more observations, you can become more and more convinced that you're right about a particular conjecture, but we're never really convinced until we prove it. And that's what we are doing over here when we're in the deductive reasoning column. So basically what we do with deductive reasoning is we start with some axioms or assumptions, and then we unravel those assumptions and say, well, if these things are true, what must be true based on that? But typically, though, when you're doing this, you have a particular conjecture in mind. So you start with some things that you're assuming, and you say, well, how can I get from what I know to be true to what I suspect is true? I'm pretty sure this is what's going on. So how can what I know get me to the outcome that I think I'm supposed to get? And so we would follow sound principles of sound logic, as we're going to discuss in this series, and we would come up with a truth. Now, if we do that over and over again from the same set of assumptions or for some axioms, which are just assumptions about perhaps an entire number system, for example, we come up with one truth and another truth and another truth. And then the collection of all of these truths weaves this beautiful tapestry. Most mathematicians, people who are interested in pure math, find it really beautiful. And so that's what deductive reasoning is. Now, when you are engaging in deductive reasoning, again, you're usually starting from P, some particular assumption, and trying to get to Q, some other consequence of that first assumption. That's what you're typically trying to do. So it may not feel like this funnel process where you start with one thing and you end up with many things. It might feel like you're starting with one or two things and then you're ending up with one thing. But we do that over and over and over again. And as we do that over and over again, we produce something much larger. And we see how all of those different truths interact with each other, and it produces something that we tend to find quite beautiful. So just for emphasis, inductive reasoning is reasoning that is supported by evidence. So we're coming up with a theory or a law, and then we run some experiment to test that theory. And when we run that experiment, we're looking for more observations to confirm what the theory or law says ought to happen. But those are just observations, and one more observation could cause us to have to throw the theory out the window. Now, with deductive reasoning, we're using logic and we're using proof. The beauty of deductive reasoning is that if your assumptions are true and your logic is flawless, then that implication, that statement that you've proven that says that if these assumptions are true, this consequence is true. That's always going to be true. Once you've proven something, you don't have to prove it again. So that is called deductive reasoning. Now, this is an old XKCD. I'll just let you read that for a second. I think it's funny. It's one of those images that I always thought was funny, especially in college as an undergraduate math major. We always get into these silly little competitions. They're not real competitions. We're not particularly competitive, but you'd say, oh, physics is better than math. Math is better than physics. You argue with physics majors. But honestly, the physics majors and the math majors that I've known have all tended to get along really well and appreciate each other's strengths, because the physicists do tend to have excellent intuition for things that are physical, for mechanical systems, often mechanical systems, while mathematicians are excellent at logic and maybe don't have that intuition for the mechanical systems that some physics majors do. But I've also had arguments with people like the chemists, and they say that, well, chemistry is the central science. It's what the title of one of those textbooks. So that's a funny little thing. This is just a reminder of what we talked about in the last video. People tend to think that mathematics is the purest of these sciences because it's not particularly applied to anything. But in being as abstract as it is, it doesn't apply to any particular thing, but it applies to a particular set of objects that behave in a certain way. And once you find an object that behaves in that way, you immediately get all the consequences of the mathematics for those particular objects. So we talked about that last time with the example from optimization. Now, when students take a theorem proving class, one of the things they often ask is, what am I allowed to assume for this proof? And it's a very good question. And my answer is this. Typically, you're going to get to assume whatever is known by others taking the same course or readers at your level. So typically, students taking this course would have a calculus background. They would also know a little bit of differential equations. They'd probably also know a little bit of pre-calculus. And there's an expectation that you would know some definitions from number theory, but we'll go over those as well. Now, other things that you're allowed to assume for the proof include just definitions of things. Now, when we talk about mathematical objects, the definition is going to tell you exactly what a particular word means. And that word is standing in for an object that tends to have a certain property. That definition tells you exactly what that property is. Now, your intuition is going to help you, and it's going to help you often. But when you use your intuition, you're tending to use that inductive reasoning that we talked about at the beginning. You're collecting evidence and you're following like what feels right when you say, this is what I actually think is going on. But we can't use intuition in our proofs. That's not the same as knowing and applying a definition. So to illustrate that, I have Magritte's The Treachery of Images. I'm sorry if I'm mispronouncing his name. I've never taken French. And actually, there are multiple names for this particular painting. And actually, what we have is, I think, a screenshot of a meme of a painting. And that painting is a person's conception of a pipe. And below that, in French, it says that this is not a pipe. I stumbled across that in a book by Douglas Hofstadter that I really love called Gödel, Escher, Bach. But that painting is a reminder that the image that we have of something is not necessarily the same as the actual thing. And we would even say that the word pipe is not the same as an actual pipe. And we have to distinguish between the reality of the object and our conception of it, our image of it, and all of those things. So I've added that for emphasis, just to emphasize that the image you have of some mathematical object, whether that mathematical object be a matrix or a function of a single variable or a prime number or an odd number or an even number, that image that you have of that object is not the same as the mathematical object itself. For our purposes, when we're writing a proof, we're going to use the definition to tell us what that mathematical object actually is. Now, the philosophers might say that the definition of a prime and an actual prime are not the same thing, perhaps, but we are going to use the definitions when we prove things, and we're going to use definitions in a number of ways. So make sure you distinguish between maybe the image of you have of something. Like, for example, you might think, oh, an odd number is a number that ends in 1, 3, 5, 7, or 9. That's good. And I'm glad that you have that intuition, and that's going to help you. That if a number ends in those digits, then we know that it's an odd number. But that's not what we want to use when we're trying to either prove that something is odd or assume that something is odd in order to prove something else. What we want to use is the definition. We'll do that instead. Now, in order to do all this, we just need a quick review. We talked about these last time. This top line is just the end with the double bars that represents the natural numbers. It's the counting numbers starting with 1, 1, 2, 3, 4, 5, and I could go on forever. That list is infinitely long. Now, if we add a 0 to that list, those are called the whole numbers, 0, 1, 2, 3, 4, 5, and so on. The integers are just like that. You just take all the whole numbers and then you add onto that list all of the opposites of the natural numbers. So -1, -2, -3, -4, and so on. Those are the integers. Now, the rational numbers are represented by this Q, and the rational numbers are all of the numbers that can be written as quotients of integers. So those are numbers of the form P over Q, where P and Q are integers, and of course the denominator is non-zero. Now, the real numbers, that's just represented by all of the numbers represented on our real line. That goes from -infinity to infinity, and includes all the rational numbers and includes some other numbers called irrational numbers as well, like square root of 17 and pi and e. Those are on the real line. And then that C with the double bars represents the complex numbers. A few other definitions that you'll probably need if you're trying to learn to prove things are these definitions of even, odd, prime, and so on. So we say that an integer x is even if and only if there is an integer k such that x is equal to 2 times k. So if x is 22, we can say that it's even, and we could say it's even because it ends in 2, or we could say 22 is even because it's 2 times 11, and 11 is an integer. So there is an integer k equals 11, such that 22 is equal to 2 times k, or 2 times 11, that gives you the 22. So this is the definition of even. We're going to talk more about this if and only if in a few videos from now, when we cover section 1.2. An integer is odd if and only if there is an integer k such that x is equal to 2 times k plus 1. Because if you take an integer, just any old integer, those could be positive, negative, or 0. If you multiply it by 2, it's going to make it even. If you add 1 to it, it's going to make it odd. So we say that a number is odd if it can be written in this form. We say that a number is even if it can be written in this form. And vice versa. If it can be written in this form, it's even. If it can be written in this form, it's odd. For natural numbers A and B, remember those are the positive counting numbers, 1, 2, 3, 4, and so on. We say that A divides B if and only if there is a natural number k such that B is equal to A times k. So we say that A divides B if A times some other integer k, or other natural number k, is equal to B. So basically, if we say A divides B, we're saying that A is a factor of B. A natural number p is prime if and only if p is greater than 1, and the only numbers that divide p are 1 and p. Different textbooks will give you different definitions for primes. In the book that we're using here, our primes are all natural numbers. So we're not going to talk about negatives being primes in this book, but I've seen other math books where they let primes be negative as well. In this book, we're only going to look at the positive primes. And we'll say a real number x is rational if and only if there exist numbers p and q, integers p and q, such that x is equal to p divided by q. In other words, if you can write x as a quotient of integers, of course, the 1 in the denominator is non-zero, so this actually makes sense. If you can do that with x, then x is rational. Now, again, you're going to be using definitions and proofs rather than your intuition. Your intuition might help you come up with what it is you want to prove. But once you've decided what you want to prove, or somebody gives you some fact and they say, prove this, you're going to be using definitions in 2 ways. Let's use the definition of an odd number to give us a concrete example. One way that you might use the definition of, let's say, an odd number is that you might assume it's true. So in the problem statement, you might be told that you're starting with an odd number, or you may have already shown that a number is odd. If you've already been told that, or you've already shown that, then you can correctly state that the number can be written in the form 2k plus 1 for some integer k. So if we're assuming that a number is odd, then we can use that as part of our assumption. Now, if we need to prove that a number is odd, so we don't actually know that the number is odd yet, but we think it's odd, we're trying to show that it's odd, the definition is going to give us something to show, something to prove. Now, this might seem very obvious. Of course, I either assume that the definition is true or show that the definition is true. But if you can keep those 2 straight in your mind, it's going to help you write proofs, and it's going to help you do a much better job. It's a very important distinction. We can't assume things are true that we're trying to prove are true. If that makes sense. If we're trying to prove that x is odd, we can't just say x is odd, therefore I'm done. My proof is done. No, we have to somehow show it using sound logical reasoning. Okay, so that's the end of our little introduction on prerequisites. Next time we're going to talk about propositions and connectives. We're probably just going to start with propositions and paradoxes next time. But we'll start with propositions and paradoxes. Then we'll talk about simple and compound propositions, talk about conjunction, disjunction, and negation. Then we'll talk about what it means for a formula, a propositional form, to be a well-formed propositional form. We'll talk about the equivalence of propositional forms. We'll do some truth tables, and we'll define the terms tautology, contradiction, and denial. And after doing all of that, that's going to give us enough to get started, enough terminology and background to get started in discussing implications. So saying, if this is true, then that is true, and what a proof of something that looks like that might look like. But first we need to define some important terms and learn about truth tables. So we'll do that next time. Thanks, guys. See you then.